Hi everyone, Eric Kraus here. I wanted to talk to you a little bit today about map datum, coordinate systems, and useful tools for backcountry planning, whether you're going out to do a recreational activity like backcountry skiing or backpacking or hiking or anything like that, or if you are a professional and do search and rescue or wildland firefighting or things like that. So we're going to talk about these and a little bit of why they are important. So let's get right into it. So first off, you might be wondering, what am I referring to when I say datum and coordinate system? Or you might have a good idea, you might know more than me. But what we're looking at is generally on most maps, you're going to have a legend area, and within that legend area, you're going to have something that says datum. And you can see here it says NAD 27. We'll go into what that means here in a little bit. And then down over here where I have this circled, you have this series of numbers in black and a series of numbers in blue. So these are different ways of telling your coordinates. So again, we'll get into all of this here in just a sec. But that's what I'm talking about with datum and coordinate systems. So let's start with datum. Datum you can think of as the shape, the size, so think acres, square feet, square miles, square kilometers, any unit of area, and the orientation. So is it directly north or is it angled at a certain degree, a certain way? So we're looking at the shape, the size, and the orientation of an area of land. There are many different types of datum throughout the world, depending on different countries and states and organizations that might have tried to create their own for specific areas. But in North America, and particularly in the United States, you're going to typically see three different types of datum. And these are the ones that you should definitely know and know what they are. So the first is going to be NAD 27, then NAD 83, and WGS 84. So that's North American datum of 1927, North American datum of 1983. And World Geodetic System of 1984. And those years are the years that these were published. Okay, so again, you can take a look at these two different map legend areas and where they say the datums that you're going to be using. So there's some key differences between these, and these are really what you should know. So when we look at NAD, so North American datum, that is only applying to North America, as to where World Geodetic System is applying to the entire world. So if you're over in Switzerland, then the North American datum doesn't really do you a whole lot of good. So every single datum has a point of origin. Okay, so this is your center mark, and then from there you are surveying relative to that center mark. So in the North American datum, both 1927 and 1983, that point of origin is a place called Meads Ranch in Kansas, and that was chosen because it is close to the center of the United States. So for the 1927 datum, that was done all by ground land survey. So you literally had people going out on foot and surveying the land using various triangulation and trigonometry techniques to figure out where they were relative to Meads Ranch, Kansas. Okay, so obviously 1927 was before the invention of things like GPS and other aerial data gathering means. So in 1983, another set was published specifically to North America. So it's the North American data in 1983. And this was an updated version where they were actually using both the land survey data that they gathered previously and also GPS and aerial data to get a more accurate measure of North America. Okay. So then we get into WGS 84. Again, this is World Geodetic System of 1984. And the point of origin for this is actually in Greenwich, England. If you're familiar with longitude, this is also where the prime meridian runs. Okay. This was published in 1984, so this was after GPS was invented, and fortunately, they were able to use that technology for this datum. and it is one of the most accurate datums available, and it's also global. So most GPS devices are defaulting to WGS84. If you have a GPS on your smartphone, that's probably going to default to WGS84. But we're going to get into why you might need to change it here in just a second. So why does it matter? And also you might be asking, well, if WGS84 is more accurate than NAD27, then why is NAD27 still relevant? It's over 90 years old. And the answer to that is that it takes a really long time to update a whole lot of paper maps throughout the world. So there are still a lot of maps in circulation that are using NAD27, others that are using NAD83, and then even more they're using WGS84. Okay, so this is why we still have to kind of know about all of these. So again, we're going to look at why does this actually matter. And here we have this point that I created on a map, and I don't expect you to be able to read this. I am certainly having a tough time myself, so I copied it up here. These are the coordinates of that specific area. This is using WGS84. Okay. Now, if we take the exact same coordinates and plot them in NAD27, so you can see that these are the exact same coordinates, and now we are on the opposite side of Clear Creek here in Colorado. So in WGS84, the coordinates plot you on the south side of Clear Creek. In NAD27, they plot you on the north side of Clear Creek. So what you can see here is that there's a little bit of a discrepancy between the two. You can have the exact same coordinate, and it's going to plot you in two different areas because the reference points are skewed just a little bit. So the biggest you're typically going to see as far as a discrepancy in datum is about 200 meters. So 200 meters might not seem like a whole lot. However, when you're talking about mountainous terrain, where you have rivers and ridgelines and forests and cliffs and all these different kind of challenging obstacles, 200 meters makes a huge difference. It can, again, in this instance, it's the difference between which side of a river you might be on. It might also be the difference of which side of a mountain you're on. So when you're planning, if you're thinking wildland firefighting or search and rescue or even backpacking or anything like that, 200 meters of mountainous terrain can make a really big difference. So that's why datum matters. Okay, so next, let's get into coordinate systems. So I gave you some examples of coordinate systems right here without a whole lot of context. So there are a lot of different types of coordinate systems. So you have degrees, minutes, seconds, you have decimal degrees, you have degrees in decimal minutes, you have UTM or Universal Transverse Mercator, and there are a whole slew of other ones. There are new coordinate systems being invented these days. There's a new one called What Three Words, which I haven't had a big chance to explore just yet. But the ones that are the most common are on this screen. So don't really worry about reading all of these things, but what I want you to take away from this is that all of these numbers are the exact same location on Earth. Okay, so it's just a different way of relaying the information of the exact same place on Earth. Okay. One thing that I do want you to look at really quick is that we have degrees, minutes, seconds listed twice, as well as decimal degrees listed twice. And the reason I have that is because we have a positive number and a negative number in this first set. And then we have a number with an N and a number with a W. Okay, and you might see these listed in certain areas, or somebody might give you coordinates and they might end it with an N, or they might begin it with an N. And what I want you to realize is that they're saying the exact same thing. Okay, so a positive number for your first set of numbers simply means that you're north of the equator. Okay, so positive and N are the same thing, and negative and W are the same thing. So this means that you're west of the prime meridian. Okay, so just keep that in mind as we move along here. So let's go into a little bit about degrees, minutes, seconds, degrees in decimal minutes, and decimal degrees, and kind of what they mean. So these are what you're going to hear referred to as lat long. So if somebody's like, hey, can you give me your lat long or your coordinates? This is probably what they're thinking. So they're going to be looking at one of these. And all of these different coordinate systems are relative to the equator for your latitude. So where you are in relation to the equator, and where you are in relation to the prime meridian, which again goes through Greenwich, England. Okay, so as we talked about earlier, positive numbers for that first set here are going to be north of the equator, and negative numbers are going to be south of the equator. And for your second set of numbers here, which is your longitude, negative numbers are going to be west of the prime meridian, and positive numbers are going to be east of the prime meridian. Okay. So another way to kind of think about particularly longitude is that you can kind of look at the Earth as being a circle. Okay, so if you're looking at it downward, so down towards the North Pole, you kind of have this circle that goes out. Okay, and we all know that a circle can be divided into 360 degrees. So again, that's why we have 180 on this side and then 180 on the other side, making 360 degrees. So each of those degrees can be broken down into 60 minutes, and each of those 60 minutes can be broken down into 60 seconds. Okay, so if you're reading in degrees, minutes, and seconds, you should really never have more than 60 minutes and 60 seconds. So as we get to this 56 seconds, we know that we are now approaching 44 minutes right here. Okay. So before we move on to UTM, I want to just go back really quick. And we just kind of talked about degrees, minutes, and seconds, but now we have this decimal degrees, and then also degrees and decimal minutes. Okay, and I don't want to get too far into these because it is a bunch of mathematical equation that goes into breaking your degrees, minutes, and seconds down into what fraction or decimal of a degree those are. Okay, so it gets really convoluted really fast. But what I want you to take away from this is that all of these coordinate system types that are broken into some type of degree are relative to your latitude and longitude. So where you are in relation to the equator and the prime meridian. Okay, so now let's go ahead and move on to UTM. UTM is one of my favorite ways of navigating on land. So it stands for Universal Transverse Mercator, and what they did here is they actually took the entire Earth, and obviously the Earth is round, and they made it flat. And this is called a projection, and this is specifically a Mercator projection. So they made it flat, and then they took the entire world and divided it into an alphanumeric system. Okay, so you can see over here on the y-axis, that is going to be our alpha axis, so alphabet, going up and down the y-axis, and then on our x-axis, we have our numeric. Okay, so up and down. So on this graphic, they were looking at the zone of 17T, so that's probably the Chicago area. I live in Colorado, so I know that my zone is 13S right over here. So 13 and S puts me right here in Colorado, and this is something that tends to confuse a lot of people at first, especially when I'm teaching in Colorado, because I'll tell them that we're in zone 13S, and they say, well, don't you mean 13N? And I say, nope, 13S. And they tend to think that that S is because they think that it should be an N because we're in the northern hemisphere, so we're north of the equator. And I have to explain to them that it's not relative. We just have the misfortune of being in S, and if we were in any other letter, it probably wouldn't be as relevant. But it's not a difference between north and south. It is this alphanumeric grid system here. So let's move on. The reason that UTM is really useful is because it's using the metric system. And this throws people off at first, so I want to kind of go over just a few key points of the metric system before we move on. So first and foremost, bear in mind that 1,000 meters is 1 kilometer. Okay, 1 kilometer is 1,000 meters. All right, just remember that for the future. And if you're not used to thinking about things in terms of meters, 1 meter is 3.28 feet, or 1 meter is 1.094 yards. Okay, so a lot of people are familiar with football, or at least what a football field looks like, and then it's divided into yards. 1 yard is 3 feet, and again, 1 meter is 1.094 yards. So when I'm in the field navigating, the way that I try to visualize distance in meters is that I know that a football field, so a football field minus the end zones is 100 yards. So from the beginning of each end zone, the middle section is 100 yards. Okay, and then each end zone is an extra 10 yards. So one football field plus one end zone, not both end zones, just one end zone, is approximately 100 meters. Okay, so it's actually about 100.5 meters. But I just kind of round down, and I remember that one football field plus one end zone is about 100 meters. So when I'm in the field navigating, that's what I try to remember because I have a pretty good idea of what a football field looks like in distance. So when you get a UTM coordinate, this is what it's going to look like. And this is not really the most intuitive thing. Normally when I show this to people, they're like, nope, 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 take me back to degrees, minutes, seconds. I don't want anything to do with it because it looks really intimidating, right? You have these huge numbers and you have letters and it's really confusing. So we're going to break this down really quick. Okay, so first and foremost, we already kind of went over finding our zone. So this first set right here, so we have 13. It's going to be our zone number, or our x-axis number. So again, we can kind of look at this grid system, and we know the 13. Boom, right there. All right, and then second number is the s. Okay, and that's going to be our x-axis, or our hemisphere row. So up here to s. So 13s right there. Excellent. So we know what zone we're in. This is really important to convey because you want to make sure that you're working off of the same zone, because if you're in different zones, it's just not going to make any sense at all. So the next set of numbers, so this entire set right here, is called your easting. Just to let you know, there is no westing. There is only an easting, is the terminology used for this first set of numbers. So just easting. And the second set is called your northing. Okay. So you have your easting and your northing. There's not a southing and a westing, just easting and northing. So now this looks really intimidating, but we're going to break it all down. Okay, so first and foremost, this letter here stands for east, and this letter here stands for north. All right, so now we have this big set of numbers right here that looks really intimidating. And we're going to break it down. We're going to go from the inside outward. Okay, so this first number here is a single meter, okay? And then we have 10 meter digit. Then we have 100 meter digits. So as we're looking, we have 7 meters. Now we have 57 meters. Now we have 257 meters. Now we have 2,257 meters. Now we have 82,257 meters. And now we have 482,257 meters. Okay, and then this last one is obviously a 0, and that stands for the million meter digit. Okay, so you might be wondering, well, what does that mean? So within every zone, so again, we know that we're in zone 13S, and that's just this big rectangle. Within every zone, you have a central meridian. That central meridian is the dead center of the zone, and that is listed at 500,000. Okay, excuse me. So anything west of the central meridian is going to be below 500,000. Anything east of the central meridian is going to be above 500,000. Okay, so on your easting, you're never going to hit a million, and you're also never going to hit zero. So just remember that you have the central meridian listed at 500,000. So from there, excuse me, we'll look at our northing. Okay, so with our northing, you'll notice that we actually do have a million digit number here. So we are, what, 4,398,045 meters north. Okay, so this is going to be north of the equator. Okay, so we know that we are 4,398,045 meters north of the equator. Okay, so rather than having a central meridian that's horizontal, everything is relative to the equator. So that should help you with reading UTM, and we'll get into a practical example here shortly. Before we do, though, I want to go into how to change units on your GPS. Okay, so the key takeaway from this entire thing is that you should have your GPS in the same datum as a paper map. Or if you're going out with multiple people, or if you might be on a team of some kind, like a search and rescue team or wildland fire team, you want to make sure that everybody's working in the same datum so that you don't end up on the wrong side of a river or on the wrong side of a mountain. So pretty much every GPS unit that I've come across has some way of changing the datum. All right, so whether it is your phone, or if you have a handheld Garmin, or if you have a smartwatch that has a GPS built in, you want to try to figure out how to do this. So this is just an example using an app called Gaia GPS, and this is on my iPhone. And this is the home screen for it. And I just went down here and clicked on settings, which brought up this screen. And then I'm able to click on units right here, which takes me to my units screen. And in here, they give me the option of switching between WGS84 and NAD27 for my datums. I can go between metric and imperial for my units of measurement, and then I can go through standard or nautical on my distance. So I'm not likely to use nautical, but some people certainly are. So if you're at sea or in aviation, you might be using the nautical versus standard. And then even further down, I'm able to go in and click on coordinate type, and I can change my coordinate type to all of those ones that we talked about earlier, as well as MGRS, which is Military Grid Reference System, which we didn't get into because it's not nearly as commonly used as UTM, but it's kind of following the same principle. So again, this is how you can do it in Gaia, and most, whether it's a phone-based GPS app or a dedicated handheld GPS app like an InReach or something like that, you can typically figure out a way to change your coordinates. So make sure that you have your GPS in the same datum as a paper map before you get too far. So let's put this all together, okay? This is an example from an actual call that I was on a search and rescue team, where we got a call of an injured hiker somewhere on Mount Democrat in Colorado. So Mount Democrat it's over 14,000 feet. It's a huge mountain. That's really not a lot of data to go on. Okay, so I'm going to turn off my screen here so you can see the entire map. So, again, we got a call for an injured hiker somewhere on Mount Democrat. Fortunately, we were able to work with a cell phone company and get a coordinate. And they gave that coordinate to us in UTM. Okay, so again, we're going to kind of break this down in an easy to digest manner. So first and foremost, we know their zone is 13S, and we want to make sure that we're working in the same zone. So I'm going to look at my map, and I can see down here. See if I can draw. So down here, I have UTM zone of 13S. It came off of a cell phone, and again, we know that most cell phones are using WGS84 as the datum, so we're going to go ahead and assume that. So we have our Datum as WGS84. And then before we move on too much further, I want you guys to know that if you would like to follow along with your own copy of this map, you can actually download it by scanning this QR code with the camera on your cell phone. So most cell phones, you can just point the camera right at it and it'll bring up a website and you can click it and you can actually download this exact map off of this QR code. So if you would like to, you can do that now. If you want to pause the video, you're welcome to do that now before we move on. All right, so moving on, if you already have this downloaded, that'd be great. If not, we can just work off of here. So we're going to take a look at what all these numbers mean. Okay, and I'm going to go ahead and just plug those into the template that we had before, and we can take a look at how to read this. Okay, so we know that our zone is 13S, we already confirmed that, and now we're going to go off of our meters. So we're going to find our easting first. Okay, so again, we don't have a millions digit here, so we're going to start with 4020. All right, so we're going to try to find that on the map. And we're working on our easting, so it's going to be these numbers here. So we have 40300 and 040200. Perfect. All right, so we're going to start off right there, and this is probably the one that we're going to be referencing. And we know that the distance between this label and this label is 1 kilometer. And our halfway point, which is this line right here, is going to be our 500 meters. All right, so now we have 040272. So all we're looking at is 72 meters. All right, so that's pretty easy. So we know that we are increasing as we go eastward because we're getting closer to that central meridian of 500,000. We know that this line is 500 meters between, but more importantly, we have this handy scale down here. And fortunately, we know that this one little black piece here and one little white piece here are 100 meters because they are 1/10 of 1 kilometer. So that is 100 meters. So we can take what that looks like and just subtract a little bit off of it, and we have a good gauge for distance. So let's go ahead and consider adding about 72 meters. That puts us probably about right here for our easting. All right, so now we need to find our northing. And our northing is going to be 4,354,000. So let's look at this, 4,354,000 right there. Okay, great. So that's going to be a really easy way to refer. And now we have 992. So we are almost at 4,355,000. So we go up here, we know that's our halfway point of 500 meters. Go up here, and that is our 4355 number. And we're just below that, right? So we're 8 meters less than our 500 number. So we know that we're right there, and we decided that we were about right here. So that plots us to be right about here, right? Great. So that's using UTM. All right, now let's try using degrees, minutes, and seconds. So our blue lines here are UTM, and our black labels here are our degrees, minutes, and seconds. So we could start out, and we're looking at 39 degrees, so this is our latitude. So 39 degrees, 20 minutes, so it's going to be 20.329 minutes. All right, so let's just take a look at what this one here is, and that is 39 degrees 20 minutes, and then this next one north is 39 degrees 20 and a half minutes. So we know that we're a little bit less than half, so we're going to pull it down a little bit less than half, probably looking at right in here, I would say, for that. So 20.329, and again, this is 20.5 right here. All right, so probably right in here somewhere. Now, so our longitude, we're looking at negative 106 degrees. Good. That aligns with what we have up here. 8.18 minutes. So we have minus 106 degrees, 8 minutes. Minus 106 degrees, 8.5 minutes. So keep in mind that as to where with UTM, as we moved eastbound, the numbers were increasing, and with lat long, it's the opposite. So as we move westbound, we're going to be increasing. Okay, so minus 106 degrees, 8 minutes, and so 8.18. So, and that's 8.5. So we're kind of probably looking right in this area. Okay, so remember that we said that our latitude was right about here. We're kind of looking right in here. So let's see how we did in comparison. Our subject was actually right where this blue dot is. So we came pretty dang close. So that is how you can plot your position on the ground using a paper map. So I highly encourage you to take out any maps that you might have and look at the margins. So look out to the sides and see what numbers you have, because a lot of them have UTM coordinates as well as degrees, minutes, and seconds, or it might be degrees and decimal minutes. So take a look at what they have and just start plotting things and figuring it out and messing with it. It's super fun. So now that we did an example, I wanted to get into some really great resources that I've come across. So these are from my actual phone, and we'll just kind of go starting left to right. So starting, I've got EarthMate. This is a really great app. It pairs with my Garmin InReach, which, if you're not familiar, it's a satellite communicator that allows me to send and receive text messages from anywhere in the world. So I can pair it with my phone via Bluetooth connection and actually type out full text messages using the EarthMate app. So that's what I use that for. Next is Gaia GPS. And this is just one of the most useful things that I've come across in recent times, where these guys have taken all of the best functions from other areas and combined them into one. So there are so many different layers that you can put on top of one another. Whether it be, they have all of the National Geographic Trails Illustrated maps digitized in there, and then you can put on weather forecasts and avalanche forecasts and all this different data on top of one another right within the app. And it's really impressive. It has taken the place of my of using my InReach as a GPS, and I'm just using that as a satellite emergency communicator now. And I'm using Gaia, and I carry 2 spare batteries with me in the field so I can plug in my phone. But I mean, this is just really, really amazing for field-based GPS. So next over, I have MotionX GPS, which is also a really good GPS system. And I used to use this a whole lot until Gaia became as robust as it is. And it's largely replaced MotionX at this point for me, but I still use MotionX every once in a while. It's pretty easy to input coordinates. So if somebody else gives me their coordinates, it's pretty easy to plot them in MotionX GPS. So I still have it on there, but I'm using Gaia mostly for my phone-based navigation. So next down, which is super exciting, is Avenza PDF Maps. So this is really a game changer, because what I'm able to do is take a map like this, which I developed in Caltopo, using their desktop app, not their mobile app. And I can take this, export it as a georeferenced PDF, meaning that's a PDF where every corner is georeferenced, so it knows what the latitude and longitude is of all of the corners, and then I can scan it using the QR code and put it right into Avenza PDFs, and I have a completely custom map that shows me my location, which is really incredible. So I've used this at my job as a park ranger, and I've created emergency maps and exported them as georeference PDFs and then gave them to everybody in events and maps so they can look at exactly where they are on this completely custom map. And it's really, really cool. So highly encourage you to get it. I also use it in the field if I'm planning like a backcountry ski day and I want my partner to have a copy of the map. I'll just print one of those out and have them scan the QR code and put it right into their phones, and then we're both working off the same map. So next over, we have CalTopo app. And what I found largely is that CalTopo is a really, really fantastic desktop app. So if you just go into your selected browser, whether it be like Safari or Google Chrome or Firefox, and just do caltopo.com, you can stack all sorts of cool different layers in there. And it's really robust, and it's a really great way to make maps using your computer. And this is their app on the phone, and the app on the phone is good. By no means is it bad, but I find that on my phone, Gaia GPS is just a lot more user-friendly. On desktop, I'm using CalTopo for the most part to plan my trips. So really good to know. And then these rest are pretty much for backcountry skiing and weather. However, what I do want to outline here is that over here we have SARTopo listed. And SARTopo, if you work in the field of search and rescue, or again, something like wildland fire, or a backcountry-based profession, it has all the same functions as CalTopo, but then it has a few extras that make it a lot better for planning, especially with groups. So you can do things like make assignments and give them to people in SARTopo. And it's really easy to input people's tracks if they track themselves using GPS and put it into SARTopo. So that's really handy. And then I have NOAA on here because if you just go to weather.gov, it gives you really, really fantastic planning tools for weather where you can actually select a specific point, and it'll give you a forecast that's very detailed for that exact spot. So you don't just get this, in the area of Denver forecast, you get the exact area that you're looking at for a forecast, which is really helpful. And then the last one that I have on here is called Theodolite, which is really cool. It's this app right over here on my screen. And what that does is actually uses your camera on your phone and gives you a ton of data on the screen. So you can go in and you have your coordinates, and you can change these from degrees, minutes, seconds to UTM to whatever you want. You can do anything you want on there. It gives you your elevation. It gives you a bearing of the degree that you're looking at. You can change it between true north and magnetic north and all sorts of different things. It's really, really powerful. And then you can actually take a picture, and all this data is captured in the photo. So if you're out cataloging things, you can actually take photos and get a whole lot of extra data within the image. But another really cool feature are these slides on the side of the screen. And what this is slope angle. So this one on the left here is your horizontal axis. So if I were to move my phone horizontally, it's going to show me what the slope is in degrees. And then if I move my phone vertically up and down, it's going to show me the slope. So super, super helpful if you are out working a fire, or where I tend to use it more than anything is if I am navigating in the backcountry in the winter. One of the key variables for avalanches is the degree of slope. So I'm constantly using an inclinometer of some kind. I've started using this more and more because it's just so easy to get an accurate slope measurement using this. So really handy tool. This mostly concludes what I wanted to chat about today. But key takeaways here are that there are tons of great resources, so use these. They are all fantastic. And second key takeaway is make sure that if you're using a paper map and a GPS, that you're using the same datum, or if there are multiple people that are going to be relaying coordinates between one another, make sure that you're all in the same datum as well. Other than that, I want to thank you all for listening, and I obviously have to put in a photo of my wonderful German Shepherd Rocco. So thank you, and feel free to reach out to me with any questions. Take care and have a great night.